Hello and welcome to the third video of this video series. In this video I'll be deriving the heat transfer rate expression for a co-current heat exchange. That being said, let's go hop into the problem and figure out what a co-current heat exchanger is. Well, the first thing you have to think about before coming in is think about two different tubes. We have just one inside of the other, right? Just kind of like this. And we have two different fluids within this, both of these tubes, each at different temperatures, and they're going in the same direction as co-current means. As this happens, one of the temperatures, which is hot, goes down and turns a little bit colder, and the cold one comes a little bit warmer, right? And as this happens through the heat capacity rate and through over time, and we will then it goes through a specific area where the specific or the heat gets transferred over to the colder liquid or the colder tube. And as you can see, we have two different positions that will come into later. But as the initial cold temperature time goes on, the one that comes out is a lot warmer, and the same thing concept with the hot. It becomes colder as it comes out. And with that being said, let's go ahead and jump into this problem. We're going to start off with some basic heat transfer expressions. So I'm going to start off with dq. We're going to have two different expressions for it. One for the hot fluid and one for the cold one, right? So for the hot one, what that will look like is we would get the specific or the mass flow rate for the hot fluid, and we have to keep in mind that this should be negative because we're going from a high temperature to a lower. So we're decreasing, so this shouldn't be negative. And then we multiply it by the specific heat capacity of the hot fluid going through. And of course, multiply it by dTH, right? Differential. As you can see, that is what comes out of both of these. The addition, this one being negative, of course, and this one being positive, hence the negative sign in the hot one. And then for the cold one, it will look pretty much the same. Otherwise, we'd have a positive because we want it to be positive, and of course it's for the cold, and the specific heat capacity for the cold, and then of course dt of the cold, right? Very simple and easy. And this is where, of course, the heat capacity comes in, heat capacity rate comes in, as it is simply the multiplication of these two, right? The mass flow rate multiplied by the specific heat capacity at that those givens gives us that. So we can go erase this out, as well as for the cold, and simply state that we have negative CH multiplied by dTH, and then CC multiplied by dTC, right? Nice and easy and simple. Then also we have another expression for dq that we will use to get our final solution, and this is in terms of U, the overall transfer, or sorry, I always forget. U is the overall heat transfer coefficient. So we have U, and then multiplied by the differential area, dA, over which the heat transfer occurs, right? And then finally multiplied by the change in temperature, delta T, right? All right. And then from here, we can start plugging these different equations in, so we can get all four of them into a single expression. So we can start off by delta T. We know delta T is simply the temperature of the hot minus the temperature of the cold. Nice and simple, right? So we also know that the derivative of the delta T is the derivative of the two, right? The derivative of the hot minus the one of the cold, right? dTh minus dTc. Of course, we can use those to plug in our dq and ch's, right? As dTh is simply equal to negative dq over ch, and dTc is equal to dTh over cc. So we can go ahead and plug that in to our expression for our d delta t. Higher up, so that we get dTh, we said we get negative ch, right? Negative dq over ch. And then we have negative dTc, which is negative dq over cc. And of course, we can see we have a common factor of our dq, so we can go ahead and pull that out, so that we get is equal to negative dq of 1 over cc plus 1 over ch, right? Those are both negatives. Yes. So that is our new expression for d delta t. And then from here, what we can do is go ahead and plug in this expression in for dq, so that we can get started for all of those coefficients, right? So if we were to plug that in, we'd have d of delta t is equal, so we said we plug in this for dq, so we'd have negative u dA delta t multiplied by this expression, right? 1 over cc plus 1 over ch. Beautiful. Then the idea here, where this 1 and 2 comes in, what we're going to do is divide both sides by delta t, so that we get d delta t over delta t on this left-hand side, and we can bring out the integrals of both from 1 and 2, and then we will work from there, and everything will start coming together. So if we were to divide it by delta t, we get d delta t divided by delta t is equal to negative u of 1 cc plus 1 ch multiplied by dA. It's getting a little messy down here, so I'm going to go ahead and erase this all up and bring this equation back here, and then we'll run the integral of it. Go bring this back up here, and then kind of take it out. Okay, so now what we can do here, like I said, is we're going to run the integrals of each of these. Alright. And we're going to run them from 1 to 2, both of them. And these 2 points I've said down here, 1 and 2. Up here we can see this is point 1 and this is point 2. 1 is the inlet when it goes in, 2 being the outlet when what comes out of the co-current heat exchanger, right? With those 2 points in mind, let's go ahead and derive this expression. So we'd have 1 over delta t, the derivative of that, is ln of that basic calculus. And then we'd have ln of delta t2 minus ln of delta t1. To logarithmic scales, we get ln of 2 or delta t2 over t1, right? Because one minus the other simply equal to division. And then for this right hand side, negative u remains the same, as well as this expression, and then the antiderivative of dA is simply a. So this right hand side remains fairly similar as compared to the right or the left hand side. Divided by a, right? So that is our new expression. However, we have some issues. We almost have everything. However, we still want this with our flow rate Q. So we need to change this and get it in terms of our flow rate, right? Q. So with that said, what I'm going to do is write new expressions for CC and CH. And what I'm going to do is, if you may remember, is Q from transport and material and energy balances, that Q is equal to MCAT, right? And we'll have one for both of these. So we know that Q is equal to the heat or the mass flow rate of the hot multiplied by the specific heat capacity, of course, of the hot multiplied by delta T, right? And then same thing for the cold. And cold, specific heat capacity of the cold multiplied by delta T, right? MCAT. And of course, delta T can be rewritten as the difference between the two, right? And also MC CPC, we know again that we can replace it with these. So we can write this over. As being C for the hot multiplied by delta T. And the same for this bottom. T for the cold, delta T. Alright. And of course, these two delta T's are different for each, as for the hot, it's different than the cold. For the hot one, we have for delta T being the difference between the T, the hot, at the inlet minus the outlet. Right? For the cold, the opposite, the outlet minus the inlet. Right? And then from there, we can go ahead and rewrite these expressions in terms of CH and CC so that we can plug it back into here, right? So if you want the reciprocal of CC, 1 over CC, we get it to be this over Q, so we get temperature of the cold outlet minus temperature of the cold inlet over Q. And then for the hot, we have temperature of the inlet minus the outlet over Q. So I'm going to erase this. And then, just so I don't remember, C of the hot is equal inlet minus outlet over Q. Alright, so now I can go ahead and erase this. Oops, and plug those expressions into our equation for our reciprocals. I'm going to keep the left hand side, but we're going to equal this to, so now we'll have negative u a, and then I'm actually going to take the q out, so just to simplify things in our expression a little bit, we'll have negative u a over q, and then we have the differences between these two, right? TCO minus TCI plus THI minus THO. Right, now we can finally kind of erase this out, and then I'm just going to erase this top one too and rewrite this expression onto the board so that we can keep going with a lot of space. You're left with ln delta T2 over delta T1 is equal to negative UA over Q of TCO minus TCI plus TOI minus THO. Alright, then I can erase these two and then get started, right? Okay, so we're at a pretty good point now. We just have to do a few final things, as you may notice. We have Q, our heat transfer rate. We have our U, our overall heat transfer coefficient, and also A. The only thing we're missing is these two issues. However, you may notice we can rewrite them in terms of delta T1 and delta T2, right? If we go to my drawing, I have this temperature, the liquid at the initial minus the one, the cold initial is delta T1, and the same concept at the outer inlet with T2. So with that being said, let's go plug that derivation in. So left hand side would be still remain with ln of delta T2 over delta T1, and of course negative UA over Q. However, so we said we have THI minus TCI, find right here, THI minus TCI plus TCO minus THO, right? And you can see those fit in perfectly for our two temperatures, right? So we can go ahead and plug that in for here so that we have delta T1 plus delta T2, right? Then now we can get this in terms of Q by itself on the left hand side and bring this logarithmic scale to the right. So that we have Q is equal to negative UA. Un attimo. No, 5 minuti.
No, rimani.
Sorry about that. Okay, so if you look back, this, I don't know how I skipped over it, is not TCO minus THO, but if we flip it around, make this a negative, this becomes THO minus TCO, so we get our negative DT, or delta T2. So if we continue on, we get Q is equal to negative UA, and then of course we have multiplied by delta T1 minus delta T2 divided by ln of delta t2 divided by delta t1. Alright. Make sure that looks correct. Yes, okay, so there we have it. We have our final terms, and this, if you might notice, is a logarithmic mean. We have different types, exponentials, basic, and so on. This is a logarithmic, and it actually has, in a lot of textbooks, a different name, or it gets its own name as the log mean temperature difference just by itself. So we can rewrite this as simply Q, the heat transfer rate, is equal to the negative U, which is the overall heat transfer coefficient, and then A, which is obviously the area available for the static heat exchange, and then this that we said is the log mean temperature difference. So our overall expression for Q turns into negative UA, and this becomes, I think, the delta T logarithmic mean is kind of how it gets denoted. But there is our expression, and that is what delta T exponentially is, what our expression. And something important to notice is that this expression is also valid for a countercurrent heat exchanger. And what that is when it's not co-current, so they're going in counterwise. So one is going, one of the, either the hot one or the cold one is going the opposite direction. And as that happens, our graph looks a little bit different. What it would look like is we would have the cold one going down, same with the cold one, turning both going cold, and we can still use this expression because we use it in terms of T1 and T2, and they can apply their terms of T1 and T2 accordingly. So with that being said, that concludes our third video in this series, and I want to thank you guys for taking your time and watching these videos. I truly appreciate it, and I hope to see you in the next one.